Earth is about 10 times heavier than Mars. What is the ratio of the radius cubed of Earth over the period squared of Earth to the radius cubed of Mars over the period squared of Mars? Is it 1 to 1, 10 to 1, 1,000 to 1, or not enough information? Now let's think about this. We know from Kepler's law that r cubed equals some constant times the period squared, right? And this constant in the middle does not depend on the orbiting bodies. It only depends on this m, which is the mass of the central body, right? So for each planet, this will have the same value, which means that if we look at the ratio of these two expressions, it'll be 1 to 1. The fact that Earth was 10 times heavier than Mars was in fact a red herring. It had no effect on the question whatsoever. Question 7. This table shows information for 4 of Jupiter's moons. Find the missing entry to 3 significant figures. Now, how would we go about figuring this one out? Well, it's quite simple, really. All we have to do is remember that r cubed over t squared is a constant number for all 4 of these moons, because they're all orbiting the same central body, right? So by using the first entry in the table for Io, we can substitute in r and substitute in t and receive a constant, which for the moment I'll just call k. K for constant, of course. I was never very good at spelling. Alright, so now that we have this constant, we can use it to figure out the orbital periods and orbital radii of the other moons. For Europa, we're given an orbital radius, right? If we have the orbital radius, then we can use this equation to figure out an expression for the period. We'll be able to see that t squared equals k, which will stay the same for all moons, over r cubed. Or, if we wanted to find just t, we could take the square root. Make sense? Now, with the value of k that we calculated for Io, we can figure out Europa's orbital period. And of course, it'll have the same units as what we used initially. So putting that into a calculator, we end up with a value of 3.55 days. If the period was measured in seconds, then this answer would instead be in seconds. As long as we keep the units the same for all the calculations, we don't need to worry about changing them. All right, how about for Ganymede? Here we don't have the orbital radius, but we do have the orbital period. And once again, we can use our constant k in order to figure out the missing variable. In this case, we're looking for r, and we can see pretty easily that r cubed will equal kt squared. In order to find just the orbital radius, we'll need to take the cubed root, right? So once again, we can use exactly the same value for k that we had for Io and Europa. This will give us a value of just over 1 million kilometers for the orbital radius of Ganymede. We can use exactly the same procedure to find the orbital radius of Callisto, which will turn out to be almost 2 million kilometers. Of course, this will work for the moons of any planet, or indeed the planets around any star. Question 8. The radius of the Earth is this figure, and the Earth's mass is that figure. What is the orbital velocity at 20,000 kilometers? Now, to figure this one out, we need to find the orbital radius, which is not going to be quite the same as the altitude. To find the orbital radius, we need to add the altitude to the radius of the Earth. Now, these are given in different units. This is in meters, this is in kilometers. So we'll need to translate it to the same units before we can add them together easily. So the radius of the orbit will be 6,380 kilometers, which is the radius of the Earth, added to the altitude of the orbit, which is 20,000 kilometers. And that will give us an orbital radius of about 26,000 kilometers. So now we can use Kepler's third law in order to figure out what the orbital velocity will be. Or not Kepler's third law, sorry, our equation for orbital velocity based on centripetal force and gravitational force. Alright, so we can substitute in the mass of the Earth. We can substitute in our orbital radius. And we can substitute in the gravitational constant. That'll give us this complicated looking expression, which we'll evaluate to 3,885 meters per second. If you want that in units that you're more used to, you can translate it to kilometers per hour. We end up at about 14,000.